Math Analysis, Miss Gagliano here with section 5.3 and the shortest path. So I'd like to start off by telling you about the gentleman who discovered this. He used to be a professor at the University of Texas, and he's considered one of the original theorists in computer science. Unfortunately, he is no longer with us. Okay, the shortest path algorithm is unlike the traveling salesman. But before we start that, let's review what sort of graph does a traveling salesman refer to? Is it a Euler circuit, an Euler path, a Hamiltonian circuit, or a Hamiltonian path? If you must visit each city exactly one time and return to your starting city. So think about that. And did you say Hamiltonian circuit? Hopefully you did. Okay, so what if, though, unlike the traveling salesman, we don't need to go to every single vertex? We just want to know wherever we're at, what is the shortest path to get to any other vertex? Sounds rather simple, so why do we need an algorithm? Well, it tends to be a little confusing if you're just looking at the graph. So we're going to go through how Dijkstra came up with this shortest path algorithm. So first off, why don't you try to see if you could find the shortest way? So here's our scenario. You're in college, your dorm room is located at H, that's home, and you want to go watch the Gossip Girls because your TV stopped working. So you're going to check which friend is closest to you. So you're going to span out from your home to the friends who live nearest to you. So go ahead and try and see what the shortest path is to each of these, and all recording is the length. So put this on pause and then go back and see how you did. Okay, actually I didn't show her the answers yet, so you'll be able to check them out as we go. Okay, so here is how the shortest path algorithm works. So we're at home, and from H, you need to look and see which vertices are adjacent to H. And the numbers are on the edges, and which one can you get to soonest. So from home, you can go to Eddie's room in 1 minute. So we're going to choose to go to Eddie's room. So now what I notice is at this point, I could either leave from Eddie's room and go to vertex C, D, or F, or I could leave from my room, H, and visit rooms F, J, or L. I want to go to the nearest room. So I just found a path of length 1. So basically you're kind of go in order. Are there any paths that are of length 2? So take a look, and these are our options. We can leave from H and go down any of the blue routes, or we can leave from E. Know that we already have a length of 1 minute that we'll have to add to our times from E, and we could go to any of the yellow routes. So those are the numbers that we're heading for. So hopefully you said that you're going to choose to go to room D, or Donna's room, and you can get there in 2 minutes. Okay, so now what we're looking for is the next closest room. So you can leave from any of the vertexes that you've already visited. So you can leave from H, and that would bring you down any of the blue paths. You can leave from E, which would leave you down any of the 2 yellow paths, or you can leave from D, which would be any of these paths right here. Once again, you're looking for the shortest path, or the room that's next closest, a length of 3. Do you see any rooms that are exactly 3 away? So these are the vertices that you're considering going to, and hopefully you notice that John's room is 3 minutes from your room. Okay, so now we're going to look for paths of 4. So this time you can leave from vertices H, J, E, or D, and you're looking for anybody that is a path of 4. Hopefully you saw that you could go to Larry's room. Okay, so now we're looking for paths of 5, and you can leave from Larry's room, from John's room, from your own room, from Eddie's room, or from Donna's room. And all of the vertices that I circled in dotted red marks are where you could end up arriving at. So hopefully you notice that you can leave from your room and go to Frank's room. That takes 5 minutes. Now look around. Are there any other paths of 5 that you could have chosen? And hopefully you saw that, yes, you could have also gone from your room to Eddie's room to Donna's room over to Claire's room, and that also would be a length of 5. Okay, so now we're looking for paths of 6. So the vertices that you still need to visit are circled with little dashes around them, and see if you can find any paths of 6. And there were 2. So from there we're looking for paths of 7, There's one right there. We still need to visit vertex G. That's our only vertex left. Is there any way to get to vertex G in a length of 7? And there you have it. So we visited every vertex, and that is the shortest amount of time it takes to get to each of them. If I did ask you on the test, you would probably write down the various, like if I wanted to get to room G, you would list H, E, D, G. Okay, moving right along, you're going to try one right now. So you want to find the shortest path from Albany to Fenton and Ladue. So if we are starting in Albany, the nearest city is C. The next nearest city, if I leave from Albany, is B. It's only 3 miles away. Now I can either depart from city B or city C, and I want to go to the next nearest city. And notice that there were 2 cities that were exactly 4 away, which is D and E. So now I can depart from city B, city D, or city E, and you want to go to the next closest city. And hopefully you saw that it was G with a length of 6. So now you could depart from city G, city D, or city E. And hopefully you saw that the next closest route was to leave from D and get to Fenton. So the shortest path from Albany to Fenton is from A through B through D and to Fenton. Okay, let's keep going. So where is the next closest city from either vertex G, vertex F, or vertex E? And hopefully you saw it was to vertex H. Okay, now we can leave from vertex G, vertex F, or vertex H. Find the next closest vertex. Hopefully you found J. And now we could leave either from vertex G or vertex J, and we have 2 more cities to get to. And hopefully you saw that we would go to vertex K. And finally now we can either leave from vertex K, vertex J, or vertex H. And the shortest route from Albany to Ladue is 14, following the green path. All right, this is your homework tonight. These are the diagrams. Follow the directions in the book, and we will see you later.